Bubble set
Okay, so welcome to this another session of structure analysis. Yesterday we were taking stability, equation of equilibrium and stability. We were discussing, I think so. I'll just quickly recap what we did. I told you that the first starting point. Okay, can I have your attention please? Yeah? Okay, so we discussed what determinate structures were, indeterminate structures, and then how stability is relevant to our determinacy and indeterminacy. Okay, the determinate structure we said are those structures in which you have got number of available equilibrium equations equal to number of unknowns. Okay, so number of available equations are the equilibrium equation depending whether you have a 2D structure or a 3D structure. Sir, excuse me. Thank you. So in the case of 2D structures, we have essentially three equilibrium equations, two related to forces and one related to moment. Okay. Now, if the number of equations, number of available equations, if they are more than the unknown reactions, then it is, if the number of available equations are more than the number of available reactions, then it is unstable. Why is it unstable? Because all the equilibrium equations won't be able to, won't be satisfied. Okay, so that's common sense. If all your equilibrium equations are not satisfied, then in that case, it is an unstable structure. Okay, so you must have the number of unknowns at least equal to number of available equations. Okay, now if the number of unknowns are more than the number of available equations, then in that case we call that indeterminate structures. Okay, in your structure analysis 2, you will see how we tackle that problem, because obviously if the number of unknowns are more than the equilibrium equations, so you need more equilibrium equation, more equations. And how do you get those equations? That is from the from your elastic curve, the behavior of your elastic curve. So for example, like I just give you one example before. If for example my elastic curve is like this, excuse me sir, can I please? Okay, thank you. So I'm saying imagine this is our elastic curve. So this is a cantilever, prop cantilever beam. Okay, why do I call it prop cantilever beam, the elastic curve of prop cantilever beam? Because this is a fixed connection and this one is a pin connection. Okay, so the property of my elastic curve is, so imagine my left hand is point A and my right hand is point B. Okay, so at point A we have to work out the compatibility, what is called compatibility equation, or the equation of the elastic curve. So what is the equation of elastic curve at point A? The deflection is 0 and the rotation is 0. Isn't it? Yes. There is no rotation. However, at point B we have only, no, rotation is unknown, only the deflection is 0. You will have rotation. Look, this is, rotation is 0. What is rotation? Moment. Yes, but I mean in the case of, for example, if I have got a beam, okay, this is my prop cantilever beam, and what I was showing, the elastic curve, so, or the deformed profile of this prop cantilever beam. Yes? So what I am saying is that rotation over here is 0. Why? Because if I draw a tangent, that tangent doesn't move. It stays at the same point, isn't it? However, over here I have got some finite rotation. This is the rotation. The rotation. What do I mean by rotation? How much this deformed curve make with the original axis of the beam. This is the original axis. The black is the original axis. When you apply load on it, any sort of load, it will assume a profile. This sort of profile. Do you understand? This is the deformed profile.
Yes, sir.
So this is like I have held this tightly in this hand, so I don't allow any rotation. But this is rotation. So this rotation is allowed. Yeah. So over here we will have deflection 0, but there will be a finite rotation. And over here we will have both deflection and rotation equal to 0. So using this property, you can develop another compatibility equation and you can solve your unknowns. This you will do in detail in structure analysis too. Okay, but that's not so. Then comes so after determinate and indeterminate structures, we have stability. In stability, we have to make sure that our available unknowns are at least equal to the number of available equations, a number of equilibrium equations. Okay, not the available equation, number of equilibrium equations. So if the available unknowns are more or equal to the number of available equilibrium equations, then we have a stable structure. And we discussed, like in case of unstable structures, what do we have? We have the structure not satisfying any of the equilibrium conditions. Okay, why do we call it unstable? Why? Because some of your any of your equilibrium condition would be violated. A force in a certain direction will be violated, or moment will be violated. Okay, so that's why we call it unstable. So we had a discussion about that. Now, one thing in stability which I wanted to discuss. Okay, so in stability, in the case of stability of structure, we have we can have two scenarios. One is partial restraint. You have a partial restraint, or you have improper restraint. Okay. So what do we mean by partial restraint? By partial restraint, we mean that you have, for example, a structure like this. Yeah, and you provide a internal hinge in the middle. This becomes unstable. Okay? So this is something which is called partial restraint.
Sir, but the reactions are equal to equations.
No, the reactions are not equal to equations. How do you say reactions are equal to equations?
What reactions?
What? There are how many? This is, you have got three unknowns.
Four unknowns. Sir, one on this one is.
This is a pin. So you have got four equations. And the number of unknowns are 3. So this is an unstable structure. 3.
Sir, if we have pin on both sides.
Sorry?
Pin on both sides.
What do you mean pin on both sides?
Pin support on both sides.
Over here? Okay, so if you have a pin support on both sides, then what will happen? You will have how many reactions?
Pin on both sides.
Okay, you have got, okay, so this is also a partial. Let us do this one and then we'll put pin on both sides. If you have a roller support like this, so in this case again, you have how many equations?
Two equations.
You have got the equations stay the same. You have got 3 equations, but the available unknowns are 2. Okay, so the summation of effects will never be satisfied. So this is an unstable structure. Okay, because this will start rolling. Now, if you say if we have a structure having a pin on both sides, so this is a stable structure.
Hinge in the middle.
Okay, so yes, if you have a hinge in the middle, Okay, so in this case we have
Four reactions. Four reactions.
four reactions, four, and how many equations?
Four equations.
So we have four reactions and four available equations. Okay, so this becomes then stable. No, this, why is this unstable? Because if someone stand on it, this will start rolling. So obviously you can't stand on it. Okay? So you can't stand on it. Why? Because this will start rolling. There is nothing to stop this movement. I mean, it will start moving in this direction. So there is nothing to stop it. That's why it is unstable. This one is stable. Why? Because these two pins are providing restraint. So although this is like a link, you have provided one link, you know, a link of a chain. So this is a link, but it is stable. Okay? Do you understand my point?
Yes, sir.
Yeah, so that is, so this is not a partial restraint, this is a stable structure.
Then when some force is applied in the middle, it will cause some moment at the end, and pin support cannot.
No. What do you mean? If you apply some load over here,
Yes, sir.
huh?
Yes.
Okay, if you apply some load over here, then what will happen?
The moment will be produced at pin support at.
Why? This pin support can never take moment.
Yes, sir. That is exactly
The
what I am
moment will be
saying.
taken by the
Then
fire.
what will counter that moment?
Inch.
You have got, what will counter? This is the same thing. Look, in the middle, you can have moments. You can have moments in the middle, but you can't have moment over here.
Yes, sir. That is exactly what I am saying, sir.
Yes.
This load will produce moment, and there is nothing to counter that.
No, but how do you say the moment is balanced? Whatever moment it produces is balanced. The overall system moment would be balanced. Summation of all moment would be equal to 0. So it is more producing moment, yes, but at this section, at this section, at this section. But if you draw a free body diagram, okay, so that moment will be balanced. You don't understand my point. Like for example, I have okay, so what will happen? You will have a moment over here. Yeah? So this reaction, this time this, you will have a moment. Agreed? And that moment will become 0 when you come over here.
Yes.
So
The moment will balance.
so the moment will become 0, or either you won't have moment at all.
Yes, sir.
In this case, if you put your load over here, for example, so what will happen?
It will still balance, sir.
How can it be balanced? I mean, if you put your moment over here, what will happen? If you put your load over here, right, you will have some moment. Yeah, that moment. So this time, it would be this force time this lever arm. Okay, but as you go over there, what will happen? That moment will start decreasing. Why? Because you will have this one cancelling the effect of that, and the time you reach over here, you will have 0 moment. Okay. In the case if you have load over here, then what will happen? If you have load over here, then
It will be that arm times the reaction.
sorry.
It will be equal to the reaction into that moment arm.
Yeah, so it will be equal to your reaction times moment arm. Yeah, but essentially you will have that moment. So the moment would normally become 0. Okay?
सर ये बहुत दोनों मूवमेंट्स क्लॉकवाइज ही हैं मतलब वो भी मूवमेंट क्लॉकवाइज है जो फोर्स लगाए हैं उससे भी क्लॉकवाइज है
Sorry, sir?
उसके स्पोर्ट भी तो है
So I didn't get you.
सर आई मीन the force at the end of
Look, let us do it. you have a
कली तू ट्रांसलेटर बन जा इस क्लास में इस क्लास में तू ट्रांसलेटर का काम कर
you have a load, imagine you have got load like this. Okay? Now, this will have a component in this direction and a component in this direction. So, this one, half of it will go there, and half of it will come here. Okay? Now, what will happen? The deformed profile will be something like this. Okay? This will get deformed. Yes? And you will have excuse me, can I have a silence please? Thank you. So you will have a reaction, say imagine R1. Yeah? And that R1 will be equal to R2. Sorry, this will also be R1 because summation of fx. Sorry, this will be R2. You will have R1 and R2. Okay? Now, P by 2 times this, yes, minus R1 times this. So that R1 times this distance. Okay? So that moment, so when you come over, so there will be moment generated by this, but that will be counteracted by this reaction. And it will become 0 when you come over here. So this is, in other words, the geometry of this will change because it's like a link. Okay? This is not a small displacement problem then. It's this will be a finite displacement. Normally when we talk about structures, we say that it is a small displacement, but its geometry will change. Okay, so that if you take this as a small displacement problem, then it doesn't work. Then, I mean, it's small displacement wise, this wouldn't work. You have to go for a large displacement, which is in reality true, because you will have, this is like a chain. So you put any load on it, chain will deform, isn't it? These are two links of a chain. So that's what G. Yes.
सर आप जो मूवमेंट ले रहे हैं या आप दरमियान वाले हिंज से ले रहे हैं या पॉइंट ए से ले रहे हैं?
Wherever you want to take.
सर लेफ्ट साइड से लेंगे तो कपल नहीं बन रहे.
What? This times this. Yeah, P by 2 times say L by 2. And R1 times whatever this distance is.
सर वो तो पॉइंट से गुजर रहे हैं लेफ्ट
हाँ?
साइड.
The movement generate नहीं करेगा.
What? Sorry?
R1 will not generate the movement because it is going through the center.
No. We are taking moment about this point from the deformed profile, not from the undeformed profile. We have to take it from the deformed profile. So R1 will generate. And in reality, it is always corresponding to a deformed profile. However, in this class, we will assume because of the small displacement, we will consider it from a undeformed profile or initial profile. In your MOS, you have done beams. Okay? You have assumed that the displacement is very small. That's why you consider the axis the same, isn't it? You take your moments, everything corresponding to this axis. But in reality, it's not so. I mean, there is some difference, but that is very insignificant. That's why it's a good assumption. Okay? It's a good assumption that you consider. But in this case, particularly in this case, this is like a chord. Okay? So chord will, if you put load on a chord, it will deform. And that will be a finite deform which you can visually see. Okay? Which you can visualize. So that's why it's a finite. What is a finite displacement? common sense wise, it is that displacement or that deflection which you can visualize. Okay, and this one clearly you can visualize.
Yes, sir.
So that's why we are taking it like that. Okay, so this is our partial restraint. Okay, then we have, after this we have sorry. Okay, then we have improper restraint. Improper restraint. What does that mean? Imagine we have got a beam whose supports look like this. Okay, so you put a load, so there are 3 rollers. This is inclined like this, this is inclined like this, and this is inclined like that. Now what happens is that all your reactions, they meet at the same point. If your reactions meet at the same point, what does that mean? In engineering mechanics, if everything meeting, huh? No, what does that mean? What do we have? Yes, moment is zero, isn't it? Because there is no resultant force which will cause moment about this. This is such a small point. Everything, all the reaction are merging at one point. So, whatever resultant you have, okay, that will have zero lever out. So that means that your reactions won't satisfy which equation? The moment equation. So you must make sure that your support don't meet, all of them don't meet at the same point. That is, okay, so you should never have this thing. So if I have a load applied at some eccentricity, okay, or in other words, at some offset from one of the support, okay, then this can cause it to rotate, okay, and this will start rotating. Yeah, this beam will start. Why? Because the reactions won't give any resisting moment. Do you understand my point? So this is called improper restraint. You will always avoid this sort of restraint. Okay? Is that okay? Yes. Any question? Please ask. Yes?
Is this structure subjected to improper restraint in this figure?
This is improper. Yes, it is improper.
When all the reactions meet at a point.
When all the reactions are meeting at a point, yes. You look for a stable structure. A stable structure reaction will not meet at the same point. Okay? The resultant of all the reaction will be at some distance apart. But in this case, it will meet at the same point. Yeah. Okay, should I rub it off? Yes? Okay, so this was your first chapter. Okay, so I would like you now, guys. I would like you guys to make 3 groups for me, okay? And you guys, this is your first assignment. Okay, in the first assignment, what I intend you to do is that you guys make 3 groups. One group will make a model which is unstable. Okay, unstable. So you have to prepare and you have to demonstrate how that is unstable. So you have to make a physical model for me, showing that it is unstable. Okay, one group will make a model which is determined by 0 degree. So it is just determinate structure. Okay, and the third group will make a model which is indeterminate. Okay, so I mean, like, you have to present a model, a physical model, showing that all the reaction, how something is determinate, so how all the reactions are getting, are emerging in the model. You understand my point? So you have to tell me, if I apply the load, so you have got a moment appearing, look, this is the moment, you have got the reaction appearing, and the number of available equilibrium number of available equations are less than the unknowns, so therefore it's indeterminate. In the other case, in the determinate group, like, you will make a model for me where everything is determinate. Okay, so you will tell me, like, there are 1, 2 or 3 equilibrium equations, and the reactions which are getting generated, those are actually equal to the number of reactions. And the unstable guys will make those will make a model where you would demonstrate how it is unstable, because one of the equilibrium equation is getting violated. Okay, so when should I expect that? However you want to make it, it's up to you. But you have to make a physical model. Okay, so the CR has to send me the group numbers. Okay, divide it into 3 groups. Divide your class into 3 groups. And is that okay?
Yes, sir.
Okay, so now, okay, so this is the first chapter of your course. Okay, your first chapter is finished now. Someone asked me, like, which Hippler book, which version would we be using? So I mean 7 or 8, whichever is accessible to you guys. So that's okay. Okay, so now the second chapter is about trusses. Okay, trusses.
Sir, what is the deadline of submitting?
I think so after 10 days. So give yourself 10 days. So that means that it is the following Friday, not the next Friday, the following Friday. So that, okay. Okay. So trusses. Okay, guys. Okay. Make it. Okay. So, but you send me please the groups. Okay. So, okay, the trust structures. Now, in structure analysis, as I told you, we have lots of structures available. Okay, and so you have got a toolbox where you have got lots of structures, and you have to appreciate where to use which structure. Okay, what is and why, based on structure efficiency, based on economy. Okay, so these are the factors which you consider normally. Now, what do you think a truss is?
Only axial force.
Yeah, but why would one go for a truss structure?
The long span is.
Yes, that's right. Normally truss is just like a beam. Okay, truss is like a beam. A beam is of limited span. It's a solid structure and it is of a limited span. Why is a beam of limited span? Because it is solid. If you keep on increasing the span of the beam, you have to increase the depth also. Because you yourself appreciate that if I have got a very thin structure, okay, and I keep on making it longer and longer, what will happen? It will deform. Okay, so I won't be able to make it stand. It becomes unstable. So I have to make it thicker and thicker as I increase the length. but there is a point beyond which it's not able to sustain its own load. Why? Because if I make it too thick, yeah, that becomes too much too inexpensive, and that becomes too expensive, and it's not able to take its own load. It collapses under its own load. Okay, so for example, if I keep on being thicker and thicker and longer and longer, a stage will come that I won't be able to do that. Okay, so therefore we go for structures like trusses. The trusses, in trusses, what we do is we provide axial force. We provide members and we arrange them in such a way that they take the load axially. Okay, only the axial load is absorbed by the trusses. Now, in the case of trusses, and these members are arranged through triangulation. Okay, so you provide triangles. Okay, triangle is a stable structure. So this is just like links. You join links with one another. Okay, a link which is square, yeah, that can't take the load. It can move. Okay, so this can't take the load. So what we do is we make it a triangle, and a triangle can
torture machine.
easily take the load. So look, if I put it like this, it will take the load. Yeah, it will take the load. But what happens? It can take the load like this, but can it take the load like this? It can take the load in both the directions. I mean like this or like this, if this is a solid member. Okay, in this case it's not a solid member. Okay, it's just a elastic member, that's why it doesn't take the load. But by making it triangle, what you are doing, you will make the structure stable. Okay, so normally the trusses are made out of steel. And why is that? Yeah, because steel is very good in tension.
Yes.
Okay, steel is good in compression also, but comparatively it's good in tension. Okay, so tension is something which steel is good at. So if you arrange your links in such a way that it can take tension, yeah, that will be so that is an efficient use of structure, isn't it?
Yes.
So if my load is coming like this and I place my bar like this instead of the other way around, like for example like this, okay, so instead of like this, if my load is like this, so what will happen? This is my structure, yeah? The load is going like this, the load is like this, and I have provided my member like this. This is in compression. Steel is not good in compression, isn't it? Steel is not good. So I will make my link how? I will provide my link like this, so that I make efficient use of my steel.
Yes.
You understand my point?
Yes.
Yeah? So you provide the links in such a way. That's why this rubber band is a good demonstration for steel structures. Okay? So you provide your structure, your truss, in such a manner that it is efficiently used. So, for example, now, for example, if I have a truss structure which looks like this, okay? I've got a truss structure which looks like this. Now, I've got loads which are applied like this. So what do you think, in what direction should I put my links? In this direction or in this direction?
Crisscross manner.
Okay, first of all, what we do is we find our reaction. Okay, we find our reactions. Okay, we find our reactions. Then, how will this bend? How will it deform?
The first one's at this time.
Why should, okay, the first one in both of them should be
Yes, sir.
like this and like this. Why? Because if I cut it over here, okay,
Tension.
if I cut it over here, this is my reaction and I've got a force in this direction, so this is causing
Clockwise movement.
look, this is like this. Okay, so this force is in this direction and
Yes, sir.
this is tension. So therefore I put my brace in this direction.
Yes, sir.
Do you understand my point?
Yes, sir.
And similarly, in this one, what's going on? I have reaction in this direction, and my force will be in this direction. So I have put it in this direction. Now, how about this one?
Same as that.
Same as
Why? Why same?
sustain moment of that type.
No, not. This is not moment. This is shear.
Yes.
This is shear, isn't it?
Yes, sir.
So if I take this one, cut it over here. So this minus this, yes, would be the force which is over here.
Yes, sir.
So what would be the direction? This is this one, and this minus this will be in this direction.
Yes, sir.
Upward direction. Yes.
No, not upward, downward.
Yes.
Is this bigger or these are bigger? The reaction will be bigger, obviously.
Yes.
Why? Because the reactions are 2 and they are summation of all of them divided by 2. So this one will be smaller than this one. Okay? So on left hand side, on this side, I have force in this direction. On this side, I have this force minus this one. So
Lesser magnitude, but same direction.
The same time.
no, you can't have. You will have it in opposite direction. You have got net force in this direction, in this place, in this link. Over here, you have got net force this minus this upwards. So summation of Fy must be equal to 0. You must have another force in the downward direction. So we have a downward direction, and again we come out.
Sir, can you repeat this?
Okay, what I'm saying is that imagine we are taking this part, this part, okay? So in this over here, we have, what is the force on slightly over here? I mean slightly beyond this link, okay? So that is this minus that, which direction is upward, okay? And over here, slightly before this vertical member, it would be, if this is upward, summation of Fy must be equal to 0. So this must be downward, okay? Summation of Fy must be 0. So this must be downward. So this is up. So I will take my link, apply load up, and this one down. So again, I will have
The same.
Same time.
the same direction.
Yes, sir. Same direction.
And similarly, I come over here. Yeah. Now this minus 2 of them, but this is bigger. This is still bigger. So I will have this minus these 2. Now over here, slightly beyond this link would be in upward direction. And summation of Fy in downward direction, and I would have a
Same time.
same. So similarly, in this case, I will have something like this. 1, 2, 3, 4, 5, 6. And this one, the middle one, how about the middle one? Yeah, we can have a cross because in one direction it will be going up, in the other direction it will be going down. So I can have a cross link over here.
थोड़ा भी याद रखता है थोड़ा भी याद रखता है दोनों एक दूसरे को cancel
No, I didn't get you. How would it cancel each other? No, come on. If there is any confusion, please don't be scared of asking questions. Yes?
ए वाला रिएक्शन जो है ये इसको इस डायरेक्शन में रोटेट करवा रहा है और बी वाला अपोजिट डायरेक्शन में रोटेट करवा रहा है तो ऑटोमेटिकली वो तो मूव ही नहीं होगा ना आगे मतलब रोटेशन तो कैंसिल हो गई
Approximately, yes. The rotation is cancelled, but I mean we have to provide something. So either you provide, sometimes you provide X brace, sometimes you provide just one brace which is like this, or sometimes in the opposite direction, however you want. Okay? So that is, but these links can be arranged like this.
We cannot leave it empty.
Huh?
We cannot leave the middle one empty.
But if you leave it unbraced, then you will, what will happen? If you leave it unbraced, this will become unstable. You can never, you have to triangulate it. Okay? If you leave it unbraced, then you have to provide some fixed connection over here. Because it will sway, it will become unstable. Do you understand my point? So that is an important consideration. Now, okay, now what happens is that in the case of earthquake, it's not necessary that load comes like this. You can have loads in this direction also. So what people do then is, like you provide one like this, another one like this, one like this, another one like this, because steel can take some compression. It's not a cord. You are not attaching a cord. This is steel.
Yes.
But you have to make sure that it takes the load. Okay? This member takes the load. So you can have something like this, so a sawtooth. Okay, so you can arrange it. So you being a designer or you being a structure analyst, you have to come up with the arrangement of bracing. You can't. So now in this structure, what do you think the top chord would be? This is called top chord. Okay, this is the top chord. And this one is bottom chord. Okay, this is a top chord and this is a bottom chord. Now we have established in what mode our braces are. Okay, but what about the top and bottom chord? Yes, why? Why compression?
because the profile will be like this.
Yes, exactly. That's true. So what happens is that if you look, this is the same sort of behavior. The top chord is in compression, just like a beam. That's why I told you that this is like a beam. You are converting a beam into a truss.
Yes, sir.
Okay? So the top chord is in compression. So this one will be in compression. And the bottom chord will be in tension. Okay? So you can have top and bottom arranged like that. Is that okay?
Yes, sir.
Now, if you have this sort of structure, okay, this sort of structure, and you are asked to analyze it, I don't know whether you have done method of joints and method of section.
Yes,
sir.
You have done that,
Yes,
yeah? So we will just very quickly review that, okay? But before starting method of joints or method of sections, you must work out where your members are having zero forces. Okay, instead of wasting your time and working it out. That's where in the first class I told you, develop your engineering judgment. So before looking at it, I can clearly see in this type of structure, this one will be 0. Summation of Fy must be equal to 0. So this is 0. This one at this joint, there is no load applied. Yes? So this one will be 0. This one has got 0 force. Straight away, this joint equilibrium has to be satisfied, isn't it? At each and every point, summation of Fx and Fy must be equal to 0. Okay, so equilibrium must be satisfied. So I have got no load over here, so this is straight away 0. Okay, I have got this load running into this. Okay, so summation of Fy, this is all together going to this one. This load is completely going there. Do you understand my point? So these joints do you understand my point?
Yes, sir.
So I am saying that go for the easiest joints and then after that start working on the other joints. Now look, this joint has got 3 members running into it, so you can't tell. You have to do summation of Fx, Fy equal to 0, and that thing you have to do before working out how much load is running into this one. Do you understand my point? Yes. So, but this one is easy. This one has got only this force running into it.
Yes, sir.
And so similarly, this one has got 0.
Yes, sir.
Summation of Fy is equal to 0. So that's how you can easily work out your
Excuse me, sir.
your forces. Okay, before starting.
Sir.
Yes.
सर ये टॉप कोड और बॉटम कोड पे हमने अज्यूम करना होता है कि लोड 0 ही ले
No, load is not 0 on top and bottom. Why do you say load is 0?
So since you said that, for example, on the first load from the left side, the only
Okay. Excuse me. I said. Okay. So I am saying that at this joint,
Yes, sir.
summation of Fy must be equal to 0.
Yes, sir.
So all the load will be running into it. But how do you say the top chord will have 0 force? Which top? Which one?
so on the left side or right side either.
No, but look, how do you know that there is a member going? Okay, this is one member. So summation of Fx, you don't know whether this has got force or not. Why? Because this force will have a component running into it. So there will be some force over there. Okay?
Yes, sir.
So I would request you that you do this sort of sense check on this. This is called a sense check. Okay? So first of all you work it out. Then you see all the top forces. Okay, if you can make a sense out of it, if the top forces, they are positive or negative, or in other words, are they in compression or tension? Okay, then see all these members whether they are compression in tension. Okay, if they are coming out to be in tension under this loading condition, obviously you have made some mistake. Okay, and you see, whether the forces over there, you have got finite forces running into it, but you will have forces in the chords. Okay, why? Because this force, you will have a component of this running into this one, and then over here, all these chords are joined with each other. In this case, we could tell why, because there was no chord at the top. Okay, so this joint is not confined vertically. This joint horizontally is confined. So if you have got horizontally confined or horizontally, you have got members on both sides of the joint, then you can't tell. Okay, it's only when you have got members at one side, and if you have got only load on the other side, no member, so then you can tell. Okay, so that is just a final thing before I end. imagine we have a truss like this one, okay, and we have provided something like this, something like this, okay. This is what we have provided, okay. Now I told you that, excuse me, I told you that one of the brace under this sort of loading, for example, if we have loading like this one of the brace will be in tension and another one will be in compression. Agreed?
Yes, sir.
Now, for example, which brace will be in compression? This one will be in compression.
Yes, sir.
And you have done buckle. In compression, what happens to steel? It buckles. So you have to, how do you avoid the buckling? You provide
Bracing.
additional bracing. So what sometimes we do is, if this is too long, you can provide additional brace like this and like this, another triangle. So I have broken this blade. I have broken the length of this one. Do you understand my point?
Yes.
So sometimes you might see something like this. This sort of arrangement might also be provided if you want to support something, like if this is a hanger and this is hanging some heavy machinery or something, okay? So, and this is not coming on these joint, on the main joint. So you provide another secondary. These are primary joints, yeah? So you provide a secondary joint, because if you don't provide this secondary joint, what will happen? You will have moment induced. This becomes a moment connection, isn't it? If you don't provide this joint like this, what will happen? You will have moment induced in this member. Or in other words, this is just like a member which is subject to load like this, okay? This AB. AB is just a member which is subject to load, and this will produce moments, isn't it?
Yes, sir.
So therefore, but trusses can't take moments. So in order to avoid that, you provide another triangle, and that's how you arrange your, you triangulate to absorb the load. Do you understand my point? Any question about this one? Is it okay? Yes, sir. Okay, sir. Thank you very much.